مرحبا بكم يا شباب والصبايا، ورحبا بكم من بيت روسي في بيروت لحضور محاضرة دكتور سيرغي فيشناكوف تحت العنوان التقنيات الحديثة لمعالجة الإشارات في إطار عام علوم والتكنولوجيا في روسيا. كما تعلمون لم يتبقى وقت طويل على تقديم منحكم روسيا للدراسة في الجامعات الروسية رائدة عبر موقع educationrussia.com. بقي حوالي أسبوعين فقط لتسجيل على هذا الموقع، لذلك من المهم أن نتابع تعريفكم على الاختصاصات المستقبلية والاختصاصات المختلفة التي يمكنكم اختيارها ضمن سلسلة محاضرات حول الاختصاصات الجديدة مثيرة للاهتمام. اليوم سنناقش مع باحث في جامعة بحوث الوطنية معهد موسكو لهندسة الطاقة، العالم روسي ودكتور في علوم التقنية ومدير معهد تكنولوجيا المعلومات والحاسوب عمليات الرقمنة في علم حديث وطريق معالجة الإشارات الرقمية فمجالات تطبيقها. تأسست جامعة في عام 1930 وفي عام 2010 أصبحت جامعة بحوث وطنية يدرس فيها حوالي 15,000 طالب وطالبة، وتتضمن حوالي 1200 مدرس أعضاء في أكاديمية علوم روسية. تخرج من الجامعة أكثر من 200,000 متخصص، فيوجد في لبنان الكثير من خريجين هذه الجامعة. وإذا نتحدث معكم سريعا عن التصنيف الجامعات الروسية، في روسيا توجد أهم جامعتين، جامعة موسكو وجامعة سان بطرسبرغ، وبعدين 10 جامعات الفيدرالية، وبعد الجامعات الفيدرالية توجد 30 جامعة بحوث. فهذه الجامعة هي جامعة بحوث وجامعة كتير مهمة في روسيا، هي معهد موسكو لهندسة طاقة. لا أحب أن أخذ كتير من وقتكم، وما تنسوا عشان إذا تحبوا تدرسوا في روسيا على حساب حكومة روسيا لازم تعملوا تسجيل على موقع إلكتروني educationrussia.com خلال أسبوعين، فتستطيعوا أن تختاروا هذه الجامعة وهذا الاختصاص كمان. Hello, Sergey Vishnikov, and welcome. Thank you for taking the time to give this lecture for our students today. I am sure it will be very interesting and beneficial for them. Please, Dr. Vishnikov.
Thank you very much. I am just honored to represent Moscow Power Engineering Institute here in Russian Cultural Center in Beirut. And I hope that my today's lecture will be interesting and fruitful for our participants. So thank you very much. So I'm starting my presentation. So here it is. Once again, hello from Russia, from Moscow, Moscow Power Engineering Institute. Just a few words about me. My name is Siergiy Vishniakov. I am the Dean of the Faculty of the Information Technologies and Computer Science and the head of the Department of Computer Systems and Networks. I had the degree of Philosophy Doctor in Theoretical Electrical Engineer, and the topic of today's lecture is modern signal processing techniques. So I hope that we're always thinking about something digital. All the digital things are around us. So we can even say that we are living in a digital world. And when we can just try to find something digital, for example, using the simple search engine, and we'll find some pictures like digital transformation, artificial intelligence, big data, digital plants, digital twins, even digital world. We see some very fascinating, very interesting things, but it is necessary to add something. What is in common of all such things? One common thing is that each topic, each title consists of the word digital. Another important thing is that all such pictures are in blue color. I suppose the blue is something that relate to the something digital. So I hope that we'll find something interesting about the first part, about the word digital. What does it mean? And why do we think that the digital world is based on digits, on some numbers or some computations? In fact, we need just to start with some source of the information, because all such digital things are just about the information processing. We need to use some information in digital form to process it using artificial neural network or some machine learning algorithm or something else. So in fact, the interesting thing is the beginning of this long digital way. And the beginning, the source of our data is usually not very digital. When I'm looking at the mirror, I cannot see anything digital. When I'm speaking, you cannot hear anything digital. It almost all the sources of the information are not very digital. They are analog or continuous sources of the signals. So, of course, when we are speaking about some scientific things, we need to describe something more theoretically, more clear. And what is a continuous signal? We can just use very simple graph and place the pair of points T1 and T2. And we can say that we can find the infinite number of new points between within the range from T1 up to T2, infinite number. We can divide it in 2 times for infinite number of times. So it's a continuous signal. It consists of infinite number of points, infinite number of some very, very small parts. And then we can translate it into the digital form. To do this, it is necessary to perform 2 operations. Technically, it may be just one device that performs all such things, but theoretically, there are 2 different things. One is called discretization, and we can obtain the discrete signal, which consists of just several points. I note such points with small blue rounds. And the distance between points is equal to T capital, where T is called the sampling time. Another process is a quantization of the signal, and we have the quantized signal with a certain number of fixed levels that are plotted in blue. Blue lines, one corresponds to the value of delta x, 2 delta x, where delta x is a step size. So we have the quantized signal. And when we are performing these 2 operations together, discretization and the quantization of the signal, we are achieving the digital signal. In fact, when it is digital, we can just use some array in some programming language, some kind of a memory of the computer, some file to store it. And of course, we don't need to store all the information about the exact time moment, about which day of the week it was when we are discretizing such signals, which time is it, each sample of the signal correspond to, or something else. We need just to say, what is the number of the sample? it may be first, second, third sample. We don't need to remember exact time, because if we know the sampling time, we can restore the actual time for each sample. The same thing is for quantized signal, for the value. We can remember not the exact value of the signal, but just number of steps. For example, 1 step or 2 steps or 3 steps, 4, 5, 6, 5, that corresponds to the plot I have in the right position. So after all, digital signal is just a sequence of some values. Usually there are integers, positive or negative numbers. So that is a digital signal. And maybe the most important thing that we need to settle, is it possible to use a digital signal the same way as we can use the continuous one? Or in other words, can we restore continuous analog signal, the source of the information, after the digitalization, after we discretized and quantized the signal? It's an important question. So of course, it's a basic thing. It's a fundamental question of the digital signal processing and of the modern digital world. So what does it mean? And why I'm so proud to represent the Moscow Power Engineering Institute when we are speaking about the discretization of the signals, or the sampling of the signals. It's because our university, our Moscow Power Engineering Institute, is a home institute of the famous scientist Vladimir Kotelnikov, who was one of the co-authors of the sampling theorem, the very famous and very fundamental theorem that is, one can say, it's a basis of our modern digital world. Other co-authors are Whittaker, Shannon, and Nyquist. So sometimes it is referred as Whittaker, Nyquist, Kotelnikov, Shannon theorem. And academician Kotelnikov was not only just graduated from Moscow Power Engineering Institute, but he was a lecturer in our university. He was the head of one of the departments. He was the dean of the faculty of the radio engineering of our university. So this is why we are so proud to say some words about the sampling theorem, about the digital signal processing. And the sampling theorem that is described that we can choose the specific value of the sampling time t that should be less than one specific value, 1 divided by 2 times f max. And if this condition is satisfied, we can transfer the signal from analog form to discrete to digital, and we can turn back from discrete form, and we can restore all the infinite number of possible points of the analog continuous signal without any loss of the information. All the information that was represented by the analog signal may be restored. Here is just one important question. I suppose it is very important, because when we are speaking about such a basic thing as a basic sampling theorem, basics of modern digital world, what's the f max that is presented in the formula? That's something that usually we can just check Wikipedia, for example, is a maximal frequency in the signal spectrum. The next question is quite evident. What's the spectrum is? Signal, we can observe signal using oscilloscope. We can measure some, I don't know, voltage using voltmeter, current using ammeter. We can use some thermocouple to measure the temperature. Where is the spectrum? And then we are finding, why do we need to have the higher education? Because the spectrum is some kind of the term that is based on application of the thing that is called Fourier transform. Fourier transform is something that is based on Fourier series, on complex analogies, on differential equations, linear algebra. So it has very, very wide and deep roots in all such basic things that relate to mathematics. And of course, to understand deeply what's the spectrum, what the digital signal processing is, we need to study all such things. Otherwise, we can just say something about blue pictures in a search engine, no more than this. And our students, of course, they work with signal processing, and we have some kind of scientific works for our students for one-dimensional signal processing. For example, we can recognize which device is connected to the power transmission network. We can describe where and when there is a risk of the heart attack using the electrocardiography. We can use the non-destructive testing to find some faults in equipment without any influence on the work of this equipment. We can process the audio signals, maybe sounds, maybe human speech. We can use it for the speech processing, for the encoding and recognition of the natural languages. So all such things are based on sampling theorem and on basics on the digital signal processing. Of course, we are studying all such things deeply. Some problems are very interesting, they are not solved even at this moment. So we are finding very, very many interesting things in working with the one-dimensional signal. But of course, when we are speaking about modern techniques of the digital signal processing, we need to mention the multidimensional processing. Oh, of course, I cannot just present in this form, in fact, video processing or some four-dimensional signal processing, because it is just impossible simply to show this. But we can just have some examples, some tasks of multidimensional signal processing for images. One important problem is the image fusion, when we have 2, 3, 4, 5, I don't know, 10 not very good images, and we can combine them in one, but with a very good quality. In fact, that's another problem that is very important, that is very demanded by the telecommunications giants, companies, that's improvement of the image quality. Another thing is color management. It seems to be a relatively simple thing. We need just to change the colors of some photo shot or some video, but it is necessary to apply more or less sophisticated processing techniques. Of course, we need to take into account the computational costs of the process, of the processing of the signal, of the color management system. We need to take into account the price that we pay for this problem solution. Of course, the classic problems is face recognition, the pattern recognition, car or signpost recognition, something like that. Of course, there are quite typical problems, and many of our students are using such problems, descriptions of the problems in their bachelor's thesis, master's thesis. One of the modern directions of the digital signal processing, of course, in a combination with machine learning, is the emotion recognition. That is very important in one-dimensional signal processing, when we can recognize some, maybe one can say, the aggression of the speech, or maybe some humor. And the same thing is face recognition and emotion recognition using the photograph of the face of the person. So there are lots of very important and not completely solved problems, engineering problems, scientific problems, and it is very interesting and very important to join the scientific groups, to join the research centers of the great telecommunication corporations, to try to solve such problems. It is very interesting and very fruitful. Another thing that we can say about the multidimensional signals is quite important, also important thing, that how to represent multidimensional signal. For example, we all know the rectangular uniform mesh or grid, and we have some pixels of the image or something like that that are basically are placed in with the equal spaces between pixels uniformly, and each pixel has the certain number of the neighboring samples of neighboring pixels. And we can always say that, aha, that is some sort of the template. It is the same template for the whole image, for example, or for the frame of the video. But sometimes it is not very useful to use such a uniform and regular mesh. Sometimes we need to cover some signal with a more efficient way. For example, with not rectangular mesh, but with hexagonal or triangular. Or maybe mesh will be rectangular, it will be regular, but not uniform. So with different distances between different points, between different pixels of the signal. It is important for example, the image or video compression systems, for the coding of the video, for the scene recognition, for the object detection, some other problems. And now our department is working on some new idea of using of the irregular meshes that are placed here in picture D. So this figure shows the irregular mesh when we have different number of the neighbor samples for each pixel. This irregular mesh may be used to cover the signal. I'll just show it. For example, we have the initial signal, that is usual picture. It is very widely used picture for the test of the algorithms of the digital signal processing. Then we are covering it with a mesh, with such triangles. We can store the mesh data, so that means that we need to store all the coordinates of the vertices of such triangles. And then we can represent the signal. One way is just to use the information about the mesh, about the triangles. And one can say, we can recognize that there is a face of some person. We can recognize the picture, but this picture consists of very small number of elements. It is to be stored in very small amount of the memory in the computer. So we can use such a representation of the signal to store it efficiently with a very low memory consumption. And it is very important for the intellectual treatment of the images, or the application of some algorithms of machine learning or artificial intelligence. Because it is necessary to combine very, very, very large number of pictures, of images, to learn some artificial intelligence thing, such as a neural network, convolutional neural network, maybe some other thing like a support vector machine or something like that. And we can store some details of this image and make a kind of the compression that is compatible to the JPEG format, or MP3 format for audio, for MP4 for video coding. We can use such combination of different details to compress or restore the image with a different quality. The same thing is valid for three-dimensional processing. So we can just formulate how to process three-dimensional pictures or video sequences or some other things that are in fact very important for the industry. For example, we can use this original way of the signal processing to compute the electric or magnetic field in three-dimensional problems, in three-dimensional cases. When usually we need to use a large number of computations. It takes huge time, but using the appropriate method of signal processing, we can lower the cost of the computations. And for example, using this method, we computed the distribution of electric field of some high voltage equipment. That is also work for the students who attend our scientific groups, who want to model the different fields, thermal, electric, magnetic, or high frequency fields in different cases for different applications. That is also very important because it's a key thing, it's a very important key thing for the digital twins. Because when we are speaking about digital twin, it's not just a blue picture that we can find in some search engine. It is a set of very, very sophisticated nonlinear usually equations, and we need to solve such equations for different conditions, and how to solve such equations efficiently. The digital signal processing, the multidimensional digital signal processing, gives some information about how to do this, how to perform this efficiently. So sometimes we need to solve very simple problems, in fact. How to make some change in a mesh that represents the signals, that covers the signals. For example, how to exclude one triangle from the mesh, keeping all the data of the attached triangles without any change. So that is very large number of relatively simple tasks, but new, and one can say there is a challenge in the signal processing because we can apply different algorithms, different methods, we can test different hypotheses and obtain different results. And we need to judge which result is better, worse, what to do with this thing. And then after all, using such contemporary algorithms and irregular meshes, we can use all all our advantages to build the convolutional neural network by using of the very large number of digital filters, of the pooling procedures that change the mesh of the signal, and the artificial neural network. There are very important challenges that are necessary to solve. For example, for such modern digital signal processing methods, we don't know the exact number of the input samples. It will be different for different cases, for different pictures. It depends on very large number of factors of the interior or objects that are placed on the picture. And we need to use quite new, different, novel methods of the artificial intelligence, of the training of neural networks, for example. And we need to use efficient representations of the signals. Maybe we need to vectorize the signal to compute some curls or divergences of the signal or something like that. So in fact, it leads us to not very simple mathematics, to applications of the relatively sophisticated formulas. I'll just give one possible examples. We need to perform the processing of the image, vectorize it, change the mesh, apply some filters, then integrate. Oh, we can see that it's a very sophisticated formulas, very sophisticated shapes that are given in three-dimensional space. And the result will be transmitted to the inputs of the artificial neural network. So now it's one can say it's an edge of the multidimensional signal processing. And so I may conclude that I want to encourage you to study in our university, to apply to be enrolled in the students of our university, because then you get in touch with such important things in the frontier of the contemporary science, of the contemporary digital signal processing techniques. And I'll just add a few words about our university. The first, just a set of basic facts about our university, that it was established in 1930. So we've celebrated 19th anniversary the previous year. We have relatively large number of the bachelor or master's programs. And of course, the bachelor's programs are very, very basic in electrical engineering, thermal engineering, computer engineering, some other fields. And master programs are more deep in certain area. For example, signal processing or digital technologies, in artificial intelligence, or maybe in some issues on artificial intelligence implementation in power networks. We have a relatively large number of centers for supplementary education, and very large number of our students have some additional courses in different areas. So it is very important to give our students a possibility to increase their knowledge. And since 1992, our Moscow Power Engineering Institute has started status of the technical university, and since 2010, our university is ranked as a national research university. So it is the highest rank among all the Russian universities. Just about 30 universities has that rank, and Moscow Power Engineering Institute, that keeps its historical name, Moscow Power Engineering Institute, is one of such highly honored universities in Russia. Now there is more than 15,000 students are studying in our university on all such programs. And one can add that there are very large number of foreign students are in our university. And one can add that we started the training of the foreign students since 1946, and now the 65 countries are presented in our university. In fact, in my own department, one of our senior lecturers, professors, is originally from Lebanon. His name is Ali Zain. So if you study in computer science or computer engineering in our university, you'll meet him, and you may ask him in your own language. He is a specialist in the big data, databases, and so on. And one can add that our university has very great facilities, infrastructure objects, like we have the own thermal power plant. So our students, of course, mainly they who study in thermal engineering, electrical engineering, they have some laboratories in our power plant. In fact, there is only one such object own power plant. It's quite a serious power plant. In fact, it also is used in as a part of the Moscow energy distribution system. So just 2 universities in the world have their own power plants. Of course, we have very large number of cultural activities. We have our own stadium. In fact, all the buildings, all the campus dormitories of our universities, they are placed in one district of the Moscow, very close together. There is a Lefortovo district. It is just not exactly in the center, not 5 minutes to Kremlin, but I suppose 20 minutes walking to Kremlin. So it is in the middle of the Moscow. And it's a very quiet and beautiful historical district of the Moscow. And all our laboratories, all our audience, all our dormitories are placed in this local district. And one can add that we have relatively large number of programs that are taught in English. And for me, the most important part that we have the programs in English, computer engineering, and computer science. So now I'll just briefly represent this pair of programs. One is computer engineering, that is bachelor's program. So of course, I will not just say all the names of the subjects, and of course, not all the courses are shown here on this diagram. So we can just say that we have very strong mathematical part, such as math, discrete math, statistics, computational math, and so on. Of course, we have a general course of physics, the foreign language, philosophy, or some other social science. Then we have the very large number of courses that relate to the technologies of the programming. That is object-oriented or some low-level programming. One can add, of course, that we have the course of the microprocessors and microprocessor systems, system on a crystal course, or something like that. Of course, we need to know the low-level representation of the programming languages, such as assembler language for x86. Of course, we try to combine it with a very large number of courses that relate to networks, computer networks, web technologies, and of course, the important thing it is it must be presented in all computer engineering programs is the issues of the computer security. And some other things like parallel programming, specific computational systems, or multi-rate systems that also relate to the signal processing, in fact. So we are trying to observe all the aspects of the modern digital world in this program. And one more program that is totally taught in English. Of course, we have the Russian program. It is to be taught in English also. The Digital Technologies or Computer Science Master's Program. And here is a list of the most important courses that correspond to this program. It consists of some courses that is related to the hardware part and the software part. And we are trying to combine the hardware courses or software courses as elective courses for the students. So some will major in digital systems design, for example, the hardware part, or someone will major in some software part is systems of virtual and augmented reality, intellectual system, machine arithmetics, and mobile programming, computer programs analysis, and so on. So it is very, I suppose it is very important for students to have a choice which part is more close, which is more interesting. And of course, there is a large number of programs that are taught in Russian. So I'll just say welcome to Moscow Power Engineering Institute. So now I'll finalize up my lecture. I'll just want to say thank you to Russian House in Beirut. Thank you very much for this opportunity.
Thank you very much, Sergey Fishnikov, for your lecture. I'm sure that this information will help students from Lebanon choose their future profession and universities. And I want to say some words in Arabic language. يا شباب والصبايا من فضلكم ما تنسوا عشان عندكم فقط أسبوعين لتسجيل على موقع إلكتروني educationinrussia.com لمشاركة في اختيار تنافسي للحصول على منح دراسية لدراسة في أحسن الجامعات الروسية. فتستطيعوا كمان تختاروا هذه الجامعة وهذه الاختصاصات اللي كانت يعني مطروحة خلال هذه المحاضرة. وبدي أشكر جامعة ومتحدث الروسي سيرغي فيشناكوف على هذه المحاضرة ممتعة، وأتمنى لكم بالنجاح في دراسة وفي اختيار مستقبل في روسيا أو في لبنان. شكرا جزيلا، مع السلامة، ونحن نتابع مشاريعنا على صفحة Studying Russia for Lebanese. مع السلامة.